Okay, everyone. We've been learning in Chapter 8 how you can use sample statistics to test hypothesis about population parameters. And we learned in 8.2 that you could use a normal curve to test hypothesis about the population proportions. And in 8.3, we learned that you could use a t-curve to test hypothesis about the population mean. Now we're going to use another distribution called a chi-squared distribution to test hypothesis about the population, standard deviation, and variance. There are two requirements to use the chi-squared distribution for a test. One is that the sample be a simple random sample, and the other is that the population has to be normally distributed, which is a fairly strict requirement, so we may have to check the normality. The chi-squared distribution, as you can see, is not symmetric. Down here is the shape of it. It is right skewed, and it also changes according to the sample size or the degrees of freedom. So let's use our chi-squared distribution on an example here. Listed below are the heights from a simple random sample of female supermodels, and it gives all their names. There are 16 of them. Use a 0.01 significance level to test the claim that the supermodels have heights with a standard deviation that is less than the population standard deviation of 7.5. So does it appear that the heights of supermodels vary less than the heights of women from the population? Okay, well, our requirements, this does say that it's a simple random sample, so that's good. But we need to know also the population is normally distributed. We can do that with a normal quantile plot. So I'm going to take my data from my list and sort it from least to greatest. This is in my column C here, my X column. I'm going to create a count column counting these with odd numbers. And then I'm going to create proportions to the left of each data value by taking the count number and dividing by 2 times 16. So 2 times my sample size. And so I create my proportions. I'm going to use those proportions to find z-scores. And so I'm using those proportions to find z-scores in column E. And then I'm going to create a scatter plot using my x values and my z-scores. And you can see this scatter plot is fairly close to this trend line without being any kind of weird pattern. It's rather random, but it's close to the trend line. So we can use our chi-squared test here. So let's figure out what our hypotheses are. Our null hypothesis would be that the standard deviation for the supermodel heights is equal to the population standard deviation, equal to 7.5. But our claim and our alternative hypothesis is that their standard deviation is less than 7.5 centimeters. Okay, so we need to create a test statistic that'll be a chi-squared statistic. We have all our ingredients here, our sample size, our sample standard deviation, which came from Excel, our population standard deviation of 7.5, and we can use that in this formula right here to create our test statistic. So our test statistic is going to be our degrees of freedom times our sample standard deviation squared divided by our population standard deviation squared. That's what I've done here. You can see that I followed this formula right here to create a test statistic of 0.906667, and we want an alpha level of 0.01. Let's find our p-value. For the chi-squared test, the p-value, how you find it in Excel, depends on what kind of test you're running. If it is a left-tailed test, you're going to use chi-squared distribution. If it is a right-tailed test, you're going to use chi-squared distribution right. And if it's a two-tailed test, you're going to use both of them, 2 times the chi-squared distribution. You're going to compare that to 2 times the chi-squared distribution right, and you're going to take the smaller of the two values as your result. So if we look right here, this is a left-tailed test. So we're going to use our chi-squared distribution for a left-tailed test with our x being our test statistic. So we're using that test statistic that we created, and our degrees of freedom, and that needs to be cumulative. Okay, so we get a p-value, well, we get a p-value then of 1.2 e to the negative 7, and that means we take our decimal point and move it 7 places to the left, which gives us 0.00000001. So our p-value is very small. Remember, if the p is low, then null must go, and p here is definitely smaller than alpha. It's definitely lower than alpha. So we are going to reject the null hypothesis. I do want to show you that you can find critical numbers as well. And to find the critical number on a left-tailed test, you're going to use chi-squared inverse with our alpha level and our degrees of freedom. And that gives us a critical number of 5.229, which you can see is our critical number down here. This picture illustrates the problem we just worked, with the critical number of 5.229 being the cutoff of this green tail region on the left. And you can see that our test statistic is within that critical region. So we will reject the null hypothesis. So we will make a decision to reject the null hypothesis because there is evidence to suggest that the standard deviation of the heights of female supermodels is less than 7.5 centimeters. Now I do want to take just a minute to show you that you can reach the same conclusion using a confidence interval with chi-squared. You do need both the left and the right critical number, and you need your degrees of freedom and your sample standard deviation, and you can see how they created the left and right bound of this confidence interval with these formulas here, and that we got a confidence interval for this same problem of 1.3 centimeters to 3.1 centimeters. So we are 99% confident that our standard deviation for supermodel heights is within 1.3 to 3.1 centimeters, which you can see that our null hypothesis of 7.5 is not in this interval. So that would support our conclusion of rejecting the null hypothesis. Okay, I want to show you just one more example. Here we have a sample of pulse rates of 37 men from a normally distributed population that results in a standard deviation for the sample of 8.1 beats per minute for the sample of pulse rates. So if the normal range of pulse rates for adults is between 60 and 100, use the range rule of thumb that is applied to the normal range, what is the estimated standard deviation? So we do need to estimate the population standard deviation here. Let's see if our requirements are met. It is a simple random sample, and it does say it's normally distributed, so no need to run a quantile plot on this one. Let's estimate our population standard deviation. Our range is between 100 and 60, so 100 minus 60 would be 40. Divide by 4 is 10. So our estimate for our population standard deviation of pulse rates is 10 beats per minute. Okay, so we have all of our ingredients here to find our test statistic. Our sample size is 37, degrees of freedom is 36, our sample standard deviation was given to us. We want to use a 0.05 alpha level, so let's change this alpha level. And let's find our test statistic. Remember, this is our formula. We're going to use degrees of freedom times the standard deviation for the sample squared over the standard deviation for the population. So let's make sure we've got it. The degrees of freedom, I used n minus 1 times the sample standard deviation squared divided by the population standard deviation squared. Looks good. Let's just change our alpha to 0.05. Okay, now we're going to find our p-value for this two-tailed test. So on a two-tailed test, remember, we're going to use 2 times the chi-square distribution for the left and 2 times the chi-square distribution for the right, and our p-value will be the smaller of those two values. On the left, we're going to use 2 times the chi-square distribution with our x being our 23.62, our standard, our degrees of freedom being 36, and we need to put a 1 for cumulative. So we end up with a p-value of 0.1119. And then on the right, we've got chi-square distribution right times 2, and our test stat, and our degrees of freedom. And for the right p-value, you don't need to say cumulative. So that is the right p-value. But the lower of the two p-values is the left one, which makes sense since our sample standard deviation was below 10. So we're going to use this 0.1119 as our p-value. Now remember, if the p is low, the null must go. Will we reject the p-value? Will we reject the null hypothesis here? No, we won't, because the p-value is higher than 0.05. So we will not reject the null. We will fail to reject the null. So I do want to go ahead and help you find the critical numbers, and that will be, we'll use, for the left critical number, we'll use chi-squared inverse. And since it's a two-tailed test, we have to use our alpha level over 2 and our degrees of freedom. Let's make sure we've got it. 0.05 divided by 2, and our degrees of freedom is 36. And 0.05 divided by 2, and our degrees of freedom is 36 for the chi-squared right. Okay? So you notice there are 2 ways that tell us to fail to reject the null here. 1, the p-value is greater than our alpha level. 2, our test statistic of 23.62 is between our 2 critical numbers. It's in the middle of 21.3 and 54.4. So we have to make a decision. And here we are going to fail to reject the null hypothesis. because there is insufficient evidence to warrant rejection of the claim that the standard deviation of the pulse rates of men is 10 beats per minute. Hopefully this will help you, and I will put this up on Blackboard so that you can use it on your homework. Next week after Thanksgiving, we will have a test just on Chapter 8. So focus on that and have a happy Thanksgiving.